This next module is 22.2, and we're going to use this electric field with Gauss's law to calculate what electric fields are for some simple symmetric cases. The first of these is a plane. Let me show you how this works. Remember from what we previously learned that the flux through any closed surface is equal to this closed surface. Because of course by definition E it's the integral of E times d sigma, where this is the area, or we could write it E dot A, where that's the integral of these surface elements all over the entire surface. If you know calculus, you'd use it this way. Otherwise, you'd say it's the dot product of E times all the little surface elements A. And what that is the charge that's inside divided by epsilon naught. This is Gauss's law. We're going to apply that to a plane. And watch this very, very neat calculation. We're going to take a plane, and on this plane we're going to put a charge sigma, which has so many coulombs per square meter. This is what you call a surface charge density. You remember we had also mentioned a volume charge density rho, which is coulombs per cubic meter, and a line charge lambda, which is coulombs per meter. This would be like if charges are on a wire or a long string. These would be charges spread out in a volume. But here we're going to look at charges that are spread over a surface. So I've got all these positive charges here. And they're uniformly spread since this is a conductor. And this goes out to infinity in every direction. Now I want you to imagine a cylinder. And the cylinder is going to cut right through the surface, come down here, have a bottom like this. So this is kind of like a tin can or a soup can that's cutting through this plane right here. And you can see that there's a certain amount of charge that's on the inside. Well, I'm going to let this cylinder have an area A. We can put an area A down here. It's going to have a certain height, but I don't even need that height, and you'll see why in just a minute. If this top and this bottom have an area A, then this part has an area A. And you'll notice that sigma is the coulombs per square meter. So the charge, since sigma is equal to charge per unit area, then the charge Q inside here is going to be sigma times the area. Well, what is this area? It's the area A, and we're going to multiply it by sigma. So for example, your area might be 4 square meters, and your coulombs per square meter might be 7 coulombs per meter squared. In that particular case, you can see the charge that's trapped inside the can would be your sigma, which is 7. That's your sigma, 7 coulombs per square meter, times your area of 4 square meters. The area will cancel. 4 times 7 is 28 coulombs. Well, that is the charge that's inside the surface that's bounded by the cylinder with a top and a bottom. It's a closed surface. All this other charge doesn't matter because the electric field lines from it go through it and go out again. But these electric field lines go straight up through the top and straight out through the bottom. Why is that? Well, the electric field has to go perpendicular to the plane because of symmetry. It can't aim to one side or another because the plane is the same in every direction. So the electric field must go straight away from the plane because it goes away from positive charge. Therefore, none of the electric field, this is the electric field I've drawn here, none of that electric field can go through the sides. Now what I want to compute is, I want to take E times A over this whole surface. Well, how do I do that to compute the flux? The flux is going to be E times A on the sides. But none of the E goes through the area on the sides because the cosine between the side area goes this way, the side area points this way, and E goes this way. That's 90 degrees, and the cosine of 90 is 0. And that just your intuition tells you that E is going this way, so none of it gets through the sides, so this is 0. Then I've got to add the flux that goes out through each end. Well, I've got 2 ends, so I'm going to multiply it by 2. And what is the electric field that goes out through the ends? Well, this electric field is constant this whole distance. And we don't know what it is at this point, but it's twice the electric field times the area of the end. And that is the flux that's coming through, and it's going to be equal to the charge inside over epsilon naught. But do we know the charge inside? Yeah. The charge inside is sigma times A. We've even computed it, 28 coulombs. So now we see that 2EA is equal to the charge inside divided by epsilon naught, which is sigma A over epsilon naught. So what is it we get? The area cancels from both sides, and we get 2E is equal to sigma over epsilon naught, or equivalently, we get the important formula, E for a plane is equal to sigma over 2 epsilon naught. This is what we wanted to get to. For the more advanced classes, you should know how to do this derivation. For the 201-202 class, an introductory algebra level class, you can just remember this, and then you can figure out how to use it. In our particular case, you remember we computed, we looked at what sigma was, we actually computed the flux, but now we only need sigma, and you recall sigma was equal to 7 coulombs per square meter. So the electric field, E, for our particular case, is going to be 7 coulombs per square meter divided by 2 times epsilon naught. And that would be our numerical answer. You can look up epsilon naught. Now if we have a line charge, you can do a similar thing. Now I'm going to use this in another example where we have a long line of charge, and we now have lambda charge per unit length. That's so many coulombs per meter. And now we're going to we want to know what's the electric field out here at some distance. What's the electric field out here? Just like here, we wanted to know what was the electric field a certain distance away. And let me go back and emphasize, there's no distance here, so the electric field away from a plane that's infinitely large is totally constant. It does not depend upon distance. Very often I'll give you a distance and you don't even use it in this equation. It's just the charge per unit area divided by 2 epsilon naught. Well, what is the electric field some distance, let's say r out here? Well, I'm going to make again a cylinder of radius r, and now you can see this has a radius r. You can see that if I put a positive charge or a negative charge on this line, the electric field is going to go straight out, and therefore I don't have to worry about the top or the bottom areas. So the dot product of E times A on the top and the bottom is 0, and all around the sides it's totally uniform. E is the same value because it's the same distance out. So I know that E times the area, which is the side of the cylinder, is going to be equal to the total charge inside. Well, you know it's cut off if we have a height. Let's say we have a height h here. Then we know that this is lambda is the coulombs per meter, and therefore lambda times h is going to be equal to the charge, and we're going to divide that by epsilon naught. Again, using this formula that the E times A is the charge inside over epsilon naught. That's the charge inside. Remind you again of why that's true. lambda is equal to the charge per unit length. And to compute the charge, therefore, it's lambda times the length, and we got lambda times h, which is the length of this thing here. Well, how do we do this? What is the area? Well, if this thing has a distance r outward, and we look at the circumference of this, then we know that the circumference all the way around is going to be 2 pi r. Well, that's the distance around the cylinder. If we multiply that by the height of the cylinder, this is going to be equal to the area. So now we can write E times the area, 2 pi r h, has got to be equal to lambda h over epsilon naught. I took E times the area of the cylinder is equal to lambda h over epsilon naught. That's Q over epsilon naught. Now h cancels, and I can compute E, and what I get is E is going to be equal to lambda over 2 pi epsilon naught times r. This is an important equation, and you must learn this equation as well as this other equation here for your tests. If I have a parallel plate capacitor next, that's really a neat one, then you'll notice that this parallel plate capacitor will be positive and this will be negative. So the charge goes away from this one, but it goes towards this one, and from this one it goes way out here. From this one it goes towards out here. So out here, since it does not depend upon distance, the electric field of one cancels the electric field of the other, and the electric field is 0 outside the pair. Now that's assuming I have the same charge sigma, a plus sigma on this one and a minus sigma on this one, charge per unit area. So E is going to be equal to 0 here, E is going to be 0 out here. But in the middle, the two electric fields add up, and due to each plane, there's sigma over 2 epsilon naught. So the electric field inside this parallel plate capacitor is going to be equal to sigma over epsilon naught. This is inside a parallel plate, where each plate carries sigma. Incidentally, also it's a rule that if I look outside any conductor, just outside the conductor, you can prove that outside the conductor you must have the electric field is equal to sigma over epsilon naught. And that's because there's no electric field in here, so all of the electric field goes outward from that conductor where it has a positive charge all over the surface. Well, that derives these primary equations. You will use these equations in different ways to compute the electric field inside a parallel plate or due to a plane or a certain distance away from a wire. And you will find that that's very useful in the calculations that we'll do in the future.